Example number 3 for rotational kinematics, we have a grindstone rotates at constant angular acceleration. Alpha is equal to 0.35 radians per second squared. At time t equals 0, it has an angular velocity of omega naught equal to negative 4.6 radians per second, and a reference line on it is horizontal at angular position theta naught of 0. A, at what time after t equals 0 is the reference line at the angular position of 5 revolutions? So I'm going to write down all my givens first. So for letter A, I know alpha, our acceleration, is equal to 0.35 radians per second squared. I know the initial angular velocity is a negative 4.6 radians per second. And I know that our initial angular position is 0 radians. And then for letter A, it says we want to know when our final angular position is equal to 5 revolutions. Now notice how all of our units are in radians per second, but we have our final angular position in revolutions. So we want to first convert that to radians. So of course we know in 1 revolution there is 2 pi radians. So that is 10 pi radians for our final angular position. Now what you're going to do is you're just going to treat this like a linear kinematics problem. So we want to think about the equation that you have. Of course, we want the time t. We want an equation that has acceleration, initial velocity, and then a delta x, in this case delta theta, but a change in position or displacement, and a time. So the equation that we want is that delta theta is equal to omega naught times t plus 1/2 acceleration, angular acceleration, times t squared. The equation that you're used to is delta x is equal to initial velocity times time plus 1/2 at squared. Same equation, but here we have it in rotation form. So here we get final minus initial for our angular position. So that is 10 pi radians equals our initial angular velocity for negative 4.6 radians per second times time plus 1/2 angular acceleration is 0.35 radians per second squared times time squared. So this is a quadratic. So when I'm going to multiply 0.35 by 1/2 and then rearrange a little bit. So I get 0.175 t squared minus 4.6 t plus 10 pi, which is 31.4, is equal to 0. And then using quadratic formula, I get x equals negative b plus or minus square root b squared minus 4 times a times c, which is a negative 31.4, my bad. And this negative 31.4 all over 2a. So I like to do everything under the square root first. So we have a 4.6 squared minus 4 times 0.175 times negative 31.4. When you take the square root of that whole thing, you end up getting 6.57. So we get 4.6 plus or minus 6.57 divided by 0.35. And so here they specifically say that we want to find at what time after t equals 0, which means that we want a positive time here. So we can see that if we subtract 6.57 from 4.6, we'll get a negative time, so we only are going to add. So 4.6 plus 6.57 divided by 0.35, we end up getting x, or time, is equal to about 32 seconds. So that is our answer for letter A. So for letter B, it says describe the grindstone's rotation between t equals 0 and 32 seconds. So we know at 32 seconds, we just found that at 32 seconds, the reference line is at a positive 5 revolutions. Okay, that's a positive displacement of 5 revolutions. So what happens here is that we can see that the initial angular velocity is a negative. So originally, the grindstone is going in the negative direction, which is clockwise, but our acceleration is counterclockwise because it's a positive. So originally at time t equals 0, the grindstone is going in a clockwise direction, but slowing down. At some time that we don't know yet, the grindstone stops and then turns around and goes in the counterclockwise direction and speeds up. Now, at time t equals 32 seconds, it is then going to be at a position of 5 revolutions or 2 pi radians. So that's kind of our description of the rotation. So letter C, it says, at what time t does the grindstone momentarily stop? So there has to be a time where we stop going in the negative direction and start going in the positive direction, because again, initial angular velocity is negative and angular acceleration is positive. So we have to start, we're accelerating in the positive direction. And we know that our final displacement is positive. So we know that we have to turn around at some point. So for letter C, we want to know when we momentarily stop. So that means our final angular velocity is 0. Again, we know initial was a negative 4.6 radians per second, and our angular acceleration was a positive 0.35 radians per second squared, and we're looking for time t. So the equation with initial and final velocity, acceleration, and time, of course, is final velocity equals initial velocity plus acceleration times time. You're very used to seeing this equation. It's just the first basic equation, but in rotation form, of course. So this is 0 equals a negative 4.6 plus angular acceleration 0.35 times time. So we get 4.6 equals 0.35 t. Time ends up being 4.6 divided by 0.35, which is 13.14 seconds. So for a more accurate description for part B, we would say that the grindstone slows to a stop at 13.14 seconds and then starts moving in the counterclockwise positive direction.